We are going to see question number 5, part A for the 2022 paper. So first I'll explain the question briefly and then we'll see how to answer the question, some parts of the question. So there is a spring hanging. The spring constant is given to be K naught for the spring. It is attached to a ceiling. A lightweight hanger is attached to the lower end of the spring and the motion detector is placed on the floor facing upward direction under the hanger. The bottom of the hanger is 1 meter above the motion detector. So this is the motion detector kept here and it measures this object here. Whatever is the height of the object from the detector, it will be measuring that and recording that. So a 0.5 kg object is placed on the hanger. Okay, so this is like a hanger here, the hanger. And a 0.5 kg object is placed on the hanger, is allowed to come to rest, and the spring is then stretched downward at distance d naught of the equilibrium and release the time t equal to 0. The motion detector records the height of the bottom of the hanger as a function of time, as shown by the graph here. So the detector is measuring the height of this object from the detector and recording and then plotting that height with time. Okay. So this is time here and this is the height. Okay. So what is happening here? I'll explain. So I'll explain the graph. This is the spring. Okay. In the natural length, where nothing is attached to the spring, it is like this. Okay. And this is the surface, the level of the detector. When nothing is attached, the detector, the height is 1 meter. When nothing is attached to the spring. Once you are attaching the mass 0.5 kg and simply releasing it, the weight of the mass will pull down the spring by some amount and the mass will rest like this. It is simply hanging down, right? This height is the equilibrium height from the detector level. And from the graph, it is clear that it is 60 centimeters, right? The equilibrium position here is at 60 centimeters from the ground here, from the detector. So I can say this is 0.6 meter is the equilibrium level. So this here is the equilibrium level. Now it is being pulled down by some amount. What is that amount? It's d naught. This object is being pulled down by a distance of d naught from here, like this. So this is d naught. Okay. Below the equilibrium position, it is stretched down and then it will start doing SHF, oscillating above the mean position. With the amplitude d naught, it is going to have an amplitude of d naught. Right. Now from the graph you can see what is the deviation from the mean. It is 5 centimeters up and down, to and fro from the mean. That means the amplitude is 5 centimeters. It is clear from the graph. I can see that the weight has pulled down this mass by this much amount. Okay? The natural length and the equilibrium position. How much is this? This is 0.4 meters. The spring got elongated by 0.4 meters due to the weight of the object hanging, right? In the first part, the question is asking what is the value of the spring constant K. I can see that the weight pulled down the spring by 0.4 meters and the spring force is given by K times. If I make a free body diagram of the object here, Upwards, there is K into the elongation, that is 0.4, is balancing the weight mg of the body here in the mean position, in the equilibrium position, this level. That is this level in action. These two forces are equal and balance them out to find out the value of K. K is equal to mg upon 0.4. M is given to be 0.5. So this is 9.8 times this. This is equal to 9.8 into 5 upon 4. That is approximately 12.25. The unit will be Newton per meter. So the unit of A is newtons per meter. That is equal to 12.25 newtons per meter. That is the value of K we are getting for the first part.